All right, so since we did not get a chance to go all the way through this PowerPoint today, I wanted to go ahead and make a screencast and post this so that you can have all the notes and get caught up this week. So let's go ahead and talk about Lewis structures, shapes, and polarity. Now, Lewis structures we've been working on, and Lewis structures are going to be a really important part of you being able to determine the polarity of a molecule and the shape of a molecule as well. So let's talk about that. VSEPR, VESPR. This stands for valence shell electron pair repulsion theory. And this is a model that we use to help us see why molecules make the shapes they make. So all of these electrons, because they all have the same charge, negative charge, they are repelled by each other. So they try to orient themselves in such a way that they're as far away from each other as possible. And so this is how you get the shapes. And the lone pairs are trying to get away from the bonds are trying to get away from each other, from the lone pairs. Everything is trying to get spaced out and away from each other. Now, in our class, we are only going to look at molecules that have up to 4 domains. So in other words, 4 things attached to the central atom. Now, I have a little flow chart here for you that really does make this a lot easier, and so that it kind of reduces the guessing. And there is a couple of things on here, if I can get the pen to work, that you can go ahead and scratch out. So we are not going to cover any of the hybridization. So all these places that talk about hybridization, you can just scratch out. Now, notice that the very first thing you're going to do in order to determine a shape is, first of all, draw a proper Lewis structure. Now, once you have done that, make sure you can determine what is the central atom. Once you have done that second part, then you can start using this chart and you can ask the first question, which is how many things are attached to the central atom in the molecule? And those things can either be atoms or lone pairs. So what you're going to do is, once you've determined how many things that is, so let's say it's 3, we're going to come down here to the next question, which is how many of those things are lone pairs? So if you have 3 things, 3 domains, you can either have no lone pairs, 1 lone pair, or 2 lone pairs. No lone pairs will give you the shape trigonal planar. And let's see if I can get that. Nope, not going to change for me. That is so awesome. Okay, we'll just deal with what we have. So if you have 3 domains, so in other words, 3 things attached to the central atom, and none of them are lone pairs, then the shape is going to be trigonal planar. If one of those things is a lone pair, then the shape is bent. And if 2 of those things are lone pairs, well, now the shape is linear. And notice that lots of times these shapes get reused. So we see linear used when there are 3 domains, but 2 of them are lone pairs. We see linear also used here when there's 2 domains and 1 is a lone pair. We see linear used here when there is 1 domain. Linear is even used here when there are 4 domains and 3 of them are lone pairs. So some of these shapes get used time and time again. So please notice, in reality, the number of different shapes you have is linear, trigonal planar, bent, tetrahedral, and trigonal pyramidal. Okay, so you really only have 5 different shapes to learn, but what you do need to memorize is how many domains, how many of those domains are lone pairs, and then what shape goes with that. All right, moving on. Maybe we'll move on. Okay, here we go. Okay, so here is another chart that maybe you find a little bit more helpful. Once again, if we look at this in terms of how many things are attached to the central atom, so we can either have 2 things attached, 3, or 4. We see that we have either bonding groups, which are atoms that are attached to the central atom, or those lone pairs. And what you're really interested in is right here, the molecular geometry. And we see once again those same shapes: linear, trigonal planar. And trigonal planar, we'll see right here. So what we see is that the central atom and the other 3 atoms attached to it are all in the same plane. So it makes it a nice triangle. Bent, pretty much just like it sounds. Instead of having a nice straight line like we see here, instead what we have is that the lone pairs or lone pairs or pair is pushing down the other 2 atoms, giving it a bent shape. Tetrahedral, this makes a pyramid shape. And then we have trigonal pyramidal. So because there is now this lone pair on the central atom, it pushes the other 3 molecules apart. So a good example of this is ammonia, NH3. A good example of this would be methane, CH4. Let's see, what do we have here? This one, this bent where you have 4 domains and 2 of them are lone pairs, this would be, let's make that better. That would be water. And I'm trying to think, what do we have here? Boron. Usually molecules with boron would be your trigonal planar. So like we have here, boron trifluoride. This one, let's see. A good one here, this would be carbon dioxide would be a good one for that. This one, I'm trying to think of a good one here. I haven't thought of anything for this one, but if I do, I will come back to it. All right, so now that we've looked at shape and we looked at how to determine the shape, now let's talk about polarity of the molecule and how we can determine if a molecule is polar or nonpolar. So first of all, what is polarity? So we use the word polarity a lot in our everyday language. We say that people are polar opposites of each other. And we're just talking about people who are very different from each other. They think very differently. And in the context of chemistry, polarity means there is an uneven distribution of electrons between 2 atoms in a bond or within the entire molecule. So let's look at that. Polar bonds versus polar molecule. So you can have this uneven or unequal distribution of electrons within a bond. And in order to determine that, we're going to look at the electronegativity of each one of the atoms, subtract them, and see what that difference is. If that difference is less than 0.5, then we're going to say that the bond is nonpolar covalent. And nonpolar meaning that electrons are shared evenly or very close to evenly. And then if the electronegativity difference is between 0.5 and, the 1.9, sometimes you might see this at 1.8, then we're going to have polar covalent. So now we have an unequal sharing of electrons. And once you get higher than 1.8, 1.9, then it is not covalent at all. The bond is actually ionic. So, polar bonds. When you determine that a bond is polar, you should also indicate which atom in the bond is pulling the electrons closer to itself. Scientists do this by using the lowercase Greek letter delta with either a positive or negative sign. You will also use an arrow with the head of the arrow pointing to the more electronegative atom in the bond. So what we would have here, when this bond between hydrogen and oxygen, hydrogen is definitely less electronegative and then the oxygen. So this is what you would have. And then you would draw an arrow where the head of the arrow points towards the the partial negative side, and then you'll see this little plus sign, this little tail, or slash, maybe that's a good way of putting it, on the tail of the arrow. And that is always going to be at the partially positive end of that polar bond. All right, so let's practice this some more. So this would probably be a really good time for you to just stop the video and try this on your own, and then press play and check your answers. So for the first one, it's between hydrogen and sulfur. And notice that I've already put the electronegativity differences here. And with this one, we're going to get electronegativity difference of 0.4. Okay, so that is definitely something that is going to be, so we're going to draw it like this. Oh, nope, we're not going to draw it like that. Oh. And we're going to see if I can get this to erase. There we go. All right, so let me try that again. We have a hydrogen and we have sulfur. And we know that that difference is going to be about 0.4. So that's not very polar, but we would see that the sulfur is definitely more electronegative than the hydrogen. And then we would draw that also like this. Now, it doesn't matter if you put the arrow on the top and the partial positive, partial negative on the bottom, just as long as you have them labeled correctly. All right, so then for this one with our fluorine and carbon, once again, what we would see here, and let's see if I can get this to erase. Nope, not going to erase. So this one is going to go this way because clearly the fluorine is the most electronegative element on the periodic table. So that one is definitely going to be the partially negative, while the carbon is going to be the partially positive. All right, so then you have carbon and silicon. And so I'm going to come over here and do that one. And we have carbon and silicon. And the carbon is more electronegative than the silicon. And we do this one more time, where we have the nitrogen and the oxygen, and we can draw it like this. There we go. Okay, so once again, we see that oxygen has the larger electronegative value, therefore it is going to be the partial negative end. All right, so that was for polar bonds. Now let's look at polar molecules. So a molecule, so just because this molecule has polar bonds in it does not necessarily mean that it's going to end up being a polar molecule. So you do have to look at some other factors in order to determine the polarity of the molecule and not just look to see if you have polar bonds in there. So once again, in order to determine the polarity of a molecule, the first thing you have to do is draw a proper Lewis structure. And once you have your Lewis structure made, then you can use this little question tree or to help you determine the molecule. So let's look at a couple of different molecules. And I'm going to start here with CH4. This is known as methane. And this would be drawn like this. And one more hydrogen. Okay. So the very first question that you're always going to ask is there a lone pair of electrons on the central atom? And for this particular Lewis structure that I've drawn on the left, the answer is no. There are no lone pairs. So then you're going to go to the second question, which is the central atom surrounded by the same atom? And yes, it is. It is surrounded by hydrogens. Therefore, this one is going to be a nonpolar molecule. Now let's try a different one. Now let's try NH3, known as ammonia. And that structure would look like this. So once again, we go back to our decision tree and we ask our first question, is there a lone pair of electrons on the central atom? And yes, there is. So once right there, since we answered yes to that first question, we're going to go ahead and say that this is a polar molecule. Okay, so that's how you determine the polarity. Here's some different examples. HCl, this is hydrochloric acid. This would be a polar molecule because there it is attached, it's two different things. And don't forget, along this chlorine would be all of those lone pairs. There's the ammonia that I was telling you about, and I'm going to just go ahead and draw in the lone pairs. And this one where we have CH3Cl. And notice that they have also drawn the arrows here for you so you can see where the electrons are being pulled towards. So in hydrochloric acid, the electrons are being pulled towards the chlorine. In ammonia, they're being pulled towards the nitrogen. And then in this one, the electrons are being pulled towards that chlorine, which is much more electronegative. So here's some examples of some nonpolar. So here's your boron trifluoride. And no lone pairs, and you have symmetry. You have the same atom surrounding the central atom. And then you have carbon tetrachloride, and once again, no lone pairs, and also we have the same atom surrounding the central atom. All right, So let's look at these and determine if they are polar or non-polar. Once again, this is a great opportunity for you to just stop the video, draw these structures yourself, and then determine if they're polar or non-polar. Press play again and see if you got the answers right. So this Lewis structure for hydrofluoric acid would look like this. And because we have all these lone pairs on the fluorine, then yes, this is going to be polar. All right, let's do H2O. Let's do water. And water has two sets of lone pairs. And those two sets of lone pairs of electrons are definitely pushing down on those hydrogens to give it that bent shape. And so because of those lone pairs on the oxygen, once again, we have a polar molecule. Ammonia, we just did this one, and so we know already that ammonia is polar. And carbon tetrafluoride. So this one, I'm going to come over here, draw it over here. And what we see, I'm going to be drawing lots and lots of dots all around these fluorines, lots of pairs. And last one right there. So once again, look at that central atom after you've drawn your Lewis structure. There are no lone pairs on the central atom, and all the atoms surrounding the central atom are all the same. Therefore, we can say that carbon tetrafluoride is non-polar. All right, last but not least is carbon dioxide. And let's see if I have some space here to put it in. And then we're going to have those lone pairs on each oxygen. Now, once again, no lone pairs on the central atom, and the central atom is surrounded by the same atom. So this one is non-polar. Now, carbon dioxide is a great example of where we end up having a polar bonds. So we have these polar bonds in a non-polar molecule. So this is a great example of just because you have polar as bonds does not necessarily mean that you have a polar molecule. And clearly, as we see, as we've drawn the structure, carbon dioxide is non-polar. All right, and that is it. If you have any questions, please don't hesitate to email me, and I will see y'all in class.